Capricious theorem, which Solution proved around 1852. That is a few years before Riemann's his hypothesis, and laid out the path towards the proof of the primary theorem. And he proved this theorem with A near about 0.9213 and B about 1.05. So, at first, let's see some applications of this theorem before we talk about how we prove this. Or actually, we will talk about a proof by Analytic, which was even easier. He used Shevchev used Starling's formula in his earlier proof, but Analytic had some elementary ideas with which the proof was much easier. So here's the first application. So application 1. An expression for the f prime. Let x equal to n. That implies that pi x is equal to n. So this relationship implies that a Pn by log Pn is less than equal to n, less than equal to Pn by log Pn. And that implies that Pn, so the first inequality is 1, implies that Pn is less than equal to 1 by P n log Pn. And the second one is that Pn is larger than or equal to 1 by P n log Pn. Now, since the n prime is larger than n, so here we have 1 by b n log. Sorry, this is going outside the range, so over the everything. So this is 1 by b n log n. So about lower bound, we already have this n log n thing here. For the upper bound, we note one thing, that for n large enough, and sufficiently large, log Pn is less than any power of Pn, but if it is sufficiently large, we can assume that it is less than square root of Pn. Okay? So we put it here. So this was, well, here. So if we put it here, we get 1 by a in root Pn. Right? So that would imply that, well, here we get root Pn and if you square it, you get Pn is less than equal to n square by a square. Right? Take log on both sides and we get that log Pn is less than equal to some constant times 1. That is all what we required. Because now if we put it there, so that would imply that log Pn is less than equal to some constant c times log n. So we can just plug it in there and obtain that Pn is less than equal to some constant times n log n. So from here we obtain that Pn is less than or equal to some constant, what we denote d maybe. So small d times n. if doesn't look down very good constant, then we have LLC. So indeed, from shape we obtain bound, upper bound and lower bound for P. Now we will see the second application. So let's keep Cuvier theorem here and let's use the board again, this one for application number 2. That is Barton's postulate. What is the statement? It says that there always exists a prime between n and 2n. Right? N is an integer. So in particular, that means if there is always a prime between n and 2n, 2n cannot be a prime, and this p is, we can also take this to be larger than okay. Here we are, so we can write that this is less than equal to, we will divide everything in such intervals, say n, 2n, 4n, etc. So when, and these ones are, well, if we start with some even number here, then all these should be strictly understood. Nevertheless, this will also imply that, note that Pk or Pn, well, there we are putting an index with n. So let's clear this up and write it down, what we want to write here. And Smita, do you remember what was Field's-Buck's condition?
Pn plus 1, n plus 1 is equal to Pn plus 1.
Yes.
Is it less than equals to n is equal to Pn.
Right. So we'll write it down and see what was required and what would have been the. So let's first write down the idea of Barton's postulate and how one gets past Barton's postulate from Cuvier theorem, and then we talk a little bit about Field's-Buck's condition. So here, first note that if you take Pn there, what do you get? No, if you take Pn here, then you know that there exists a prime between Pn and 2Pn, right? And in particular, that will imply, so Barton's postulate, that is, there exists a prime between n and 2n, that implies, in particular, that Pn plus 1 is less than Pn. Because if you take this one as your small, the boundaries, if you take Pn and 2Pn, then Pn plus 1 is lying in that. Okay. So now Field's-Buck's condition that says Pn plus 1 will over 1 by n plus 1 is less than Pn will over 1 by n. This is open condition. Now, note that this is if and only Pn plus 1 is less than Pn over n plus 1 by n, right? That is, this n plus 1, you are taking n plus 1 power on both sides. So here you are having Pn times Pn, this times 1 by n times Pn. Okay. So Pn times 1 by n times Pn. Okay. So this would have implied this if we had 2 is larger than this. So, and that would require what? If you had Pn equal to 1 by n less than 2, that would mean Pn. Wait a minute. No, you don't have this one. Sorry, you have. I mean, this would imply this if this is larger than this. Right? If this is larger than this one, then you would have that this is implying this. In case, but note that this would imply that Pn is larger than 2 power n, which is not, because we just obtained that Pn is bounded between some constant times n log n and some constant n. Actually, this type of relations, there is a important notion for that. So this is this we also write this in this manner. Yx is asymptotically equal to x by log x. This one means that it is bounded by from above by some constant times x by log x and bounded from below by some constant times x by log x. And so here in the first application, what we obtained is that Pn is asymptotically equal to n log.
In fact, if we improve the bound on A and B,
Right?
so the lower bound clearly shows that as B goes to 1, this Pn will be asymptotically
Equal to
n log
x.
n.
Right. Actually, that would be an implication of the
Right.
trigonometry. I think I should also tell you some more asymptotic notations, but with this here this so that's why you see that this one is
Not sufficient from that.
exactly. So this one is a much more stronger statement than this one.
It does this hold for like first few values of n,
Yes. This has been numerically verified for quite large number of things.
and this conjecture is for like all n.
Yes.
Sir, could you explain why it's 1 by log n?
One way you are here.
No, the one below. You were saying that you would get 1 minus epsilon times log Pn.
Oh right, because you don't need to square it anymore.
Yeah, oh, so that would be log of n by a, right?
Log
Log of n by a.
Yeah.
of n by a, right?
And that can be bounded by log n.
Yes.
Okay.
Yeah, so on both sides you are getting the coefficient to be 1.
And as a goes to 1, log a factor that anyway goes to 0.
Right. So the next thing is, about, let's introduce some more such notations and then we talk about how one goes about proving things.
So, one more question.
Yes.
It's log n minus log a in that case.
Log n minus?
I mean, once we apply log on both sides, it will be 1 minus epsilon times log Pn, which is less than or equal to log n minus log n.
Right.
But a is less than 1 in this case.
A is less than 1.
So that would mean it's log n.
It is something positive.
Yeah. So
Right. Yeah. Yes, of course. That's a valid point.
But we can
it's
like,
large enough.
yeah.
If it is rational, this becomes negligible.
Oh, I did not see log is going to negative, right?
So some more notations. Can you hear this?
So could you explain the last part you said, what would not work? And
Okay.
you stated the if and only if case, and then you were
Which
saying
one here?
yes.
Okay. So you require this one, right, for proving the for the to be true. Now, note that here we had two coefficients. So if this would have been larger than this, then it is following from there. But we are saying that it is not, because if you have this one larger than 2, then would require Pn to be larger than Pn, which is not, because Pn is asymptotically of this size. So this would work. notations as we just introduced that assembly equality. So it's also the notations. So we write if x is this is the big O notation. Big O of Tx. If x by dx remains bounded, well, we will use all this big O, small o, etc. for terms tending to infinity. Otherwise, it is also so. If your x is tending to a particular value, these are also a value notation. But for us, it will tend for all these x's being sufficiently large. So we are just sitting in that. So fx by dx is bounded by constant for all x by dx. So this is result C if x is equal to infinity. And this was the first thing. The second thing is that if x is smaller of x, that is if x and dx goes to 0 as x goes to well, of course, I will assume x is and here that is small of x just means that if you take the ratio, this is not only bounded by something, it's going to 0. The third one is the one that we just talked about. Well, there is also some shorthand notation for these ones. Or equivalently, if x is less dx. Okay? And this one, for this one we don't have such a thing. But well, one more thing is that if suppose these are functions of more variables and say fxy and gxy. Okay. So it's like if we keep y fixed, or it could be that if it is, well, what I want to say is that these are, let's write it down here. So we may have that fxy is, okay, maybe the function if its distribution is already depending on y. So if y is big O of oy gx. This means that this function would be bounded by some constant as a function of gx, and that constant will be depending on y. So O sum y just means that this constant is not an absolute constant, it's depending on y. And the same for small y as well. Small o as well. So then if x is of the size gx. Well, before that, we already seen this. This is if x is bounded by some a times gx, a times gx, or all sufficiently large. Then if these constants are depending on some other parameter, we write sub, this equality sub that parameter here. And the fourth one is that if x is of the order gx, if fx by gx is equals to 1 as x goes to so these notations we will use often.
So that one does not need a mod.
Which one?
The fourth one.
The fourth one?
Yes. Just asking. I mean, does that mean f of x by gx or?
Well, no, here we use the absolute term because this constant is that it is a positive constant. And it is just fx by gx.
Do we take g to be a positive function? Like
Yes,
non-negative?
of course, here, if we are writing big O of gx, we are taking gx to be
Or you could put mod gx.
yes.
You could put mod
Mod
gx.
So now about the idea of the proof of Scherzius theorem, but nevertheless, before finishing this the proof of the Scherzius theorem, we'll also do we'll also see Nairs argument. Here's a small homework for you. Before we begin Nairs argument, we were this integral from 0 to 1, so u power j minus 1 and 1 minus u or k minus j du is to be 1 by j in j for all j in 1 whatever. So just prove this identity, and as you mentioned, this could be also obtained from order statistics. If you have the CDM of the jth order statistics on one hand and the PDF on the other hand, you can integrate the PDF to get the CDM, and now if you specialize into some value, you will get this identity. But it would be also done directly. So this is just a beta integral, and the value of this will be given by some gamma function. So if you have same gamma function and beta function, from there you can also obtain this. So proof. The results of this 2n Cn. If you recall last time, we were considering 12 plus 1 Cn, and this time that was for the upper bound of the product of the primes up to k. Now you can actually guess whose idea was this. It was this proof was again by Erdős. So now consider the prime divisors of the at first by Vp of a function. Well, even before defining what is the evaluation of n, perhaps you already know that this is this binomial coefficient is the largest one in the expansion of 1 plus 1 over 2n. Right? So this is bounded above by 2 power 2n. And how many terms are in the expansion of 1 plus 1 over 2n? there is 12 plus 1.
12 plus.
So the average is 2 power 12 by 12 plus 1. So we are going to use these two things, and we are going to also consider the PID valuation of this. Now, how do we define this? CPM, the PID valuation.
Highest power.
Yes, the largest power of E, which divides. Now, perhaps you have already seen this formula, this called Lenz's formula. That this is given by the sum over N divided by PK, the flow rate. So, this is called Lenz's formula. Says that VP in factory is just the sum over the flow rate in by K running from 0 to infinity, but this yeah, after finite case this is going to be 0. And the proof of this is trivial.
Counting.
Yeah, let's go counting. This is sum over, say, M running from 1 to n, summation K running from 0 to infinity, P power K dividing n, and here you have the number of constants, the number of things which divide n. But note that there, this K cannot be larger than log n base p. Right? So this is not an infinite sum, but it's a finite sum. If you wrote this. And since both of these sums are finite, you can interchange them without any problem. Summation P running from 0 to log P n, and inside you have summation n running from 1 to n. Here summing over n1, and this one said pk dividing n. Right? Now, how many multiples of pk are there between n to between 1 to n? Those are exactly this. So that's how we get that this is summation k running from 0 to log p n by. So using this, we will get the VP, the PID valuation of fluency. And also, we can actually use a better identity here, invalid here, but at first consider this one. P2 when choose number. So what is this?
P is a prime. Yes.
P is some prime less than 12. So this is sum over K running from 0 to Now 2n is p, and inside we have 2n by pk minus 2 times. Well, what is this? If you expand this, this will be factorial by n factorial square. Okay? So here you have 2 times n by. Now note one thing, that 2x minus 2x for any positive x, this x values were 0 or 1. If you have instead nx and nx here in boxes, that will take the values between 0 and minus 1. Okay. And so this is in 0 and 1, and when it is 0 and when it is 1,
It's an integer, it's 0.
if it is an integer, yes of course, but even for other things,
For in z over z n to n plus half,
yes,
it would be 0.
exactly,
And from n plus half to n plus 1,
yes,
it will be 1.
sure. So it is like this is half, this is 1, and if the fractional part of it falls in there, strictly inside there, not with half, okay, then it will be 0, otherwise it's 1. So that in particular implies that the value of this is either 1 or 0. So in particular that means this sum is bounded above by this one. So this is less than log p plus n. Wait a minute, if it starts from 0, well, but it doesn't start from 0, that was a mistake, right?
1.
It starts from 1, right?
Oh.
Yeah, we're not counting the number of number of times 1 is dividing, but the number of times p is dividing. P is dividing. This is. And yeah, then we have this, that is x bounded above by log 2n plus p. So that in particular would imply that, well, one more thing, that this prime p should be less than 2n. I mean, for otherwise both of these is zero for all values of p. So this is true for all p less than. Also, one more thing, that 2n choose n is always divisible by the primes between n and 2. For all p such that n less than p less than n. So with these two things, we are going to estimate this one. The first one is this and the second one is this. So that would imply
For each prime between n and 2n, they appear exactly once.
for yes, exactly. These are all these primes are appearing exactly once. So when you choose n, the first one says that all this, the powers of all the primes which are less than 2n and which are dividing 2n chosen is bounded above by this one. So this is less than product over all the primes is 2n p, and so the VPN was what, log p less than 2n, that is pi of 2n. Okay. And from here, what we get? We'll note that each of these primes were larger than n. And how many such primes are there? Well, pi of 12 minus pi of n. So that means, let's write it there. So we are having also a lower bound for this. It is larger than n or pi of 2n minus pi of n. So we are having an upper bound and lower bound of 2n chosen in terms of the prime bounding function, both on the right hand side and the left hand side. And here we had two other variables, right? So now we can compare this lower bound with the upper bound there, and this upper bound with the lower bound there. So that's the idea of the let's wipe some part of the board, maybe this one. Comparing the left hand pole at first the right hand side of this, the left hand side there, what do we get? Well, actually, this would compare it and we can simplify this a little bit more. So the left hand side is this one here, and this would be less than or equal to 2n power sine 20. Right? Take logs. So this is 2n log 2 minus log 2n plus 1, and what you have there, pi 2n times log 2n. So divide this by log 2, and this will be less than or equal to pi 2n. Yeah, so you are having this 2n by log 2n that we go for, but there are except log 2 there is also this one which actually is much smaller than this. So you can you can bound it by, so this would be, what I want to say is that this would be larger than some constant times this by this, but we can get it more clear in this manner. Note that the left hand side of this equality, you could replace it by 2n because you have 2n less than 2 power 2n by 2n plus 1 for all n larger than 20. So this one, you would put right, this is 2n. So instead of comparing with this one, you would compare it with 2n instead, and this would be a little bit more clear. So we have n log 2 times, well, n log 2 would be less than or equal to what? In by 2n log 2n. That is 2n by constant here would be log 2 by 2 this times 2n by log 2n would be less than or equal to 5. Now let's check what we are getting from the right hand side. Here, so 2 power 2n is larger than this one. 2 power 2n is larger than n power. So this one was from one side and this one is from the other. That is, this is n power pi 2n minus pi n is larger than that. Take logs again. So this implies 2n log 2 is larger than pi 2n minus pi n log n. Alright, so well, we can clear this up a little more. Is this fine? The way we obtain these two things. So we have this part. So that becomes then 2 log 2 times n by log n. This would be larger than pi 2n minus pi n. So we are having two estimates. One is for pi 2n and another is for pi 2n minus pi n. Okay, so, and both of these we have opted from considering 2n choose n. The prime indices of this. So in the next class actually we will get the estimates for general x, I mean for arbitrary x with these two estimates. So we will recall that we had this one and we had this one, and from these two we will derive the thing that pi x for an arbitrary positive x is bounded between ax by log x and x by log x. So that's all for this class.
So last inequality, the product p less than 2n, p to the log 2n
Product over again, which one we
the last, yeah, the
okay, so product over
p less than 2n, product over the
p less than 2n and p power
p to the log 2n less p. This is less than 2n to the.
okay, so each of the factors are 2n because it's p log p.
Each p is less than 2n.
Each p is less than 2n, and note that each of these factors are equal to 2n, right? Because we are taking the log base symbol, and then how many primes? Exactly 5.